Hi all. Now let's continue with trying to understand vanishing and exploding gradients. Vanishing and exploding gradients is a very important concept when we actually go to deeper and deeper architectures, as they can cause great problems with learning. Many of you probably have already heard vanishing and exploding gradients in the context of recurrent neural networks, and this is not surprising, as recurrent neural networks are one type of very deep architecture, as we'll see in a later course. So trying to give some more context, after Alex researchers tried to understand if there are ways that we can actually train deeper networks and hopefully get better performance. However, the empirical observation was that in practice very deep networks stop learning after a while, so they reach inaccuracy, they saturate, and after they even unlearn. So signal gets sort of lost through layers and modules start failing. Now, in trying to understand this, it makes sense to try to understand what's going inside the modules. And as we discussed before, since we've got modular learning in deep learning, very logical thing to expect is to have consistent behavior per module. And when we say consistent behavior, we mean consistent behavior of activations and gradients mainly. So now let's try to put this now into perspective. If we check the backpropagation gradients, then we will observe that the gradient of the loss with respect to the parameters of the Lth layer are in fact depending, like if we check here in the middle terms, they're depending on a product of L Jacobian matrices or tensors. Now this is a very interesting relation because it connects the depth L with our like some gradient quantities, and in trying to figure out actually something about the gradient behavior, a very simple statistic and very important statistic is gradient norm, because it tells us, like, does the gradient become smaller, does it become larger over as a function of the neural network's depth. Since our gradient norm is connected to Jacobian matrices, multiplications of Jacobian matrices, we have to therefore focus on the spectral norm of the Jacobian matrix. So this spectral norm will basically tell us whether after the application of the module, after the application of the transformation in the module, does our input vector, like in this visual example here, does it become larger or smaller? So after we apply the transformation, what is the actual effect to the length of input? This is something that the spectral norm can actually tell us, and of course the big question is, how do we compute the spectral norm? Now the spectral norm turns out to be simply the largest of the singular values. So we can compute that with an SVD algorithm. And as a reminder, singular values are simply the square roots of the matrix eigenvalues. In trying to get some more understanding what spectral norm and what singular values stand for, to get some more intuition, we can visit this graphical example. So in this simple 2D example, we've got a transformation M that operates on the unit circle X. So this unit circle X sort of summarizes, in its blue pixels, it summarizes all the possible inputs that the transformation can receive. Now this linear transformation M, this matrix multiplication applied on these vectors in the unit circle, transform the circle into an ellipsoid. That is literally the effect of a linear transformation. They transform a unit circle to an ellipsoid, and it turns out that the singular values are the half axis of this ellipsoid. So the largest of the two is the spectral norm. Now, what does the spectral norm capture? Therefore, it captures the biggest possible change that any of the possible inputs of our transformation can sustain, right? So basically the spectral norm tells us how big of a change can we at maximum expect. In our case, for our particular case of backpropagation gradients, let's say that for simplicity we assume that each module comprises a linear operator with parameters w transforming in the input x into y, and this is followed by nonlinearity h. Now the spectral norm of our Jacobian here, of these two guys, is upper bounded from above by the spectral norm of the linear transformation times the spectral norm of the derivative of the nonlinearity. Here we assume that the nonlinearity is applied element-wise. So we have a diagonal matrix where the non-diagonal elements are 0. This is basically what the ReLU does, right? So the ReLU is applied per dimension. Now, after we combine all our modules, we can see that the gradient norm is basically upper bounded by the product of the largest singular values of each of the module. This is a very interesting quantity because it connects the gradient norm with a depth L of our neural network as well as with the singular values in our modules. This gives us therefore a tool to see what happens when we change the depth, or for different spectral norms, for different singular values for our transformations. Now let's try to basically check with some small case studies. With larger and larger like depths, if the singular values are smaller than 1, enough smaller than 1, the gradients of the loss with respect to the ELF parameters can become very, very small, and therefore they can vanish. For instance, let's say that our singular values are about 0.5 and we have only 10 layers. Then the spectral norm, the gradient norm could be in the order of 10 to the minus 5. This means very small gradients and very slow learning, therefore. This could even confuse us whether we have converged on, or whether we should stop. That can be a problem. If the singular values are larger than 1, larger enough than 1, in contrast, we could actually obtain very, very large gradients because of this chain multiplication. So for a singular value of 1.5, the norm could be up to the 10 to the power 17, which is a huge number. It means that we can actually have unstable optimization and even divergence and unlearning. To try to, one could say then, why don't we change their norms with the learning rate? That could be possible, right? Well, let's try to figure this out a bit more. What happens for different locations of the neural network? Let's say we've got a neural network, a deep one. Here's our input X, and here is our output L. So let's say this is 50 layers, deep neural network. The effects are exponential to the layer depth. So this means that layers that are closer to the output will have very few multiplications in this relation. Therefore, the relation is basically linear. The effects are not that dramatic. However, layers that are further from the loss will have much more terms in the multiplication here. Therefore, we're going to have the good old exponential growth. We're going to have very large or very small values depending on the singular values of our modules, the large singular values of our modules. So this gives an answer on why learning, like adapting the learning rate, is not necessarily the right solution. Different layers, different modules, depending on their location in our neural network, will have different behaviors. We will not have consistent behaviors anymore. Therefore, we could adapt the learning rate, but we would have to do that per module, depending on the location. And also bear in mind that a small gradient doesn't necessarily mean that we have difficulties in our optimization. It could also mean that we simply have converged towards a good solution. Therefore, the optimizer would be confused. Shall I stop because I've already converged, or shall I sort of try to have larger gradients such that I get to a reasonable minimum? That is the problem that the vanishing and exploding gradients create, and the problem of having inconsistent gradient behaviors because of that. Thank you.